Okay, let's learn about exponential growth. And lots of things increase exponentially in nature. Populations, money in a bank account, nuclear chain reactions, computer processing power, to name some examples. Now, the basic formula for exponential growth is the amount you end up with is the initial amount, the amount you're starting with, times e raised to the kt. K is called the growth rate constant and T is time. It could be hours, days, years, whatever. You'll get that from the context of the question. So here's a typical problem that uses population. In 1999, the population of a city was 16,400, and by 2009 it was 20,200. So find the exponential growth model, that function that models the population growth of the city, and use that function to predict the population of the city in 2015. Okay. So we're going to let t equal 0 be 1999. Okay, so that means my initial amount, n sub 0, is 16,400. So as things stand, I've got n of t equals 16,400 e to the k t. Now I have to find k. Well, 10 years later, it's 20,200. So I'm going to put that in right here. 20,200 equals 16,400 e to the k times 10. And if I go 20,200, 200 divided by 16, well, I keep messing that up, don't I? Divided by 16,400, that will equal e to the 10k. Since we're working with e, let's take the natural log of both sides, okay? So I'm going to do the natural log of 20,200 divided by 16,400 equals 10k, because the natural log of e to the 10k is 10k. All right, so we work that out, and I get that k, well, let's go ahead and work it out, okay? Okay, so I'm going to go natural log of 20,200 divided by 16,400. Get that. Divide by 10. And I get 0.0208444k. All right. So our function modeling the population is 16,400 e to the 0.02084t. Now, how are we going to figure out the population in 2015? Well, that's 16 years later than 1999. So I'm going to put 16 in for t. And let's work that out. Drag it over here. So I've got 16,400. And then I get my e to the x function there. 0.02084 times 16. And 22,890.5, well, we can't have a person, so we'll call that 22,891 people in the year 2015. Another example of exponential growth is when you put money in an interest-bearing account. So here's your formula for this. The amount of money you have is equal to the principal, the money you first invest, times 1 plus the interest rate in decimal form divided by the number of times you compound it per year raised to the n times t. And t in this case is always years. Okay? Okay, so let's say we're investing $1,000, annual interest rate of 6.5% for 20 years compounded monthly. Okay, so that means that P is 1,000, R is 0.065, that's 6.5% decimal form. T is 20, and since it's compounded monthly, N is 12, because monthly means 12 times per year. All right, so let's just plug everything in. So A is 1,000 times 1 plus 0.065 over 12 times raised to the 12 times 20. And I went ahead and put in my calculator, and we get $3,656.45. Let me see if I can make that big enough for you to see there. Okay, and that's dollars because we're talking about money. Now, what would the balance be if the interest was compounded daily? Would it change? Well, let's see. The only thing that's going to change from our formula is instead of N being 12, it's going to be 365. So I get 365, and that was 20 years. Okay, 20. And I went ahead and put that into my calculator and got an answer of $3,668.87. So it's a little bit better deal if you can get it compounded daily instead of monthly. Well, if it's a better deal compounding daily instead of monthly, what would it be like if you compounded it an infinite number of times per year? That's called continuous compounding, and it has its own formula. A equals P times e to the RT, fondly known as the PERT formula. So we can do an example of this, and this is actually easier to use. So let's say we've got $2,500 invested at 6.7% interest. That's 0.067 interest, compounded continuously for 10 years. So it'll be 2,500 times e to the 0.67. And let's see what that is in our calculator. And you can see I've entered it in up here, and I have $4,885.59. All right. So let me see if I can drag that out here, make it a little bigger. There you go. So that's how you do compounding continuously. And that's all you need to know for exponential growth.